Hey everybody. Today we're talking about inverse normal calculations. And when tackling this topic, I think it's really helpful to start with regular normal calculations. So probabilities for normal random variables, like any continuous random variables, are computed using the cumulative distribution function, or CDF, which gives the probability that the variable comes out to be less than or equal to the specified value. And when we're talking about the standard normal distribution, the CDF is written phi of z. The CDF takes a possible value of the variable and gives back its cumulative probability. So takes a z-score, gives back a probability. The inverse normal CDF just reverses that process. So it takes the probability and gives back the variable value with that cumulative probability. So if we're talking about the standard normal distribution, the normal CDF maps from z to p, the inverse normal maps from p back to z. The picture is the same in either case. When the probability of z is less than or equal to some specific value, little z, is equal to p, p is the area to the left of z under this graph. So phi takes the z value, gives you back the p. Phi inverse takes the p and gives you back the z. More generally, in any normal distribution, n of mu comma sigma squared, so now we have a mean mu and a standard deviation sigma, the inverse CDF takes a probability p, equivalently a percentile or area to the left, and gives back the x value for which the probability of getting a random value less than or equal to x is equal to p. Although it's possible to do inverse normal calculations using tables, it's far better to do it using technology. R is totally typical, and that's my technology of choice. The syntax is qnorm, and you feed it the probability or the area to the left of the percentile, same thing, and then the mean and the standard deviation of the normal distribution you're working in. For instance, let's find the value x for which the probability of getting a random value less than or equal to x is 0.70 in a normal distribution with mean 10 and standard deviation 2. So I've drawn a picture here. I have tried to shade, roughly speaking, the x value that has about 70% of the area to the left. And then I'll actually compute the x value using the command qnorm of 0.70, 10, 0.2. So first the probability that I'm interested in, then the mean, then the standard deviation, and I get back the x value. So the x value for which the probability x is less than or equal to x equals 0.70 is about 11.05. When computing in the standard normal distribution, that is where the mean is 0 and the standard deviation is 1, you can omit the parameters inside of qnorm. So you can just do qnorm of 0.95 instead of qnorm of 0.95, 0, 1. Although that other code works too. The z-score for which phi of z equals 0.95 is about 1.645. Here's an example for you to try. Find the 90th percentile in the standard normal distribution and illustrate with a picture. So I recommend pausing the video, giving this a try on your own before seeing my solution. So here's the picture. I drew a standard normal distribution and I tried to draw 90% of the area to the left of the value that I have indicated here on the x-axis. So the shaded area should be about 90%. Then the 90th percentile, which is sometimes denoted pi sub 90, is phi inverse of 0.90, qnorm of 0.90, it's about 1.28. So that's the 90th percentile of the standard normal distribution. Here's one more for you to try. Scores on a standardized test are normally distributed with mean 1060 and standard deviation 195. How high must a student score in order to have a 95% chance of beating a randomly selected score? So pause and give that a try. Similar picture, I've labeled an x value that has 95% of the area to the left, and then I'll compute what x is with the command qnorm 0.95, 1060, 195. So give me back the x value that has 95% of the area to the left in the distribution that's normal with mean 1060 and standard deviation 195. We get about 1381, that's the 95th percentile of scores in this normal distribution. So a student with that score will have a 95% chance of beating a randomly selected score.